Alright folks, so today we're going to do a little bit of practice with solving equilibrium concentrations from biochemical reactions. And this is essentially just a review of some of the CHEM equilibria stuff you've done before, but this time we're going to do it in a biochemical context. So I've got this problem set up that I wrote. So this is the first reaction of glycolysis, where glucose is phosphorylated using ATP by the enzyme hexokinase to generate glucose 6-phosphate and ADP. And essentially what this reaction helps the cell do is trap glucose in the cell so it can't just leak back out of the transporters. Transporters can't interact with glucose 6-phosphate, and so this traps glucose in the cell so that it can't get back out. In pretty much every cell in your body this happens except for the liver. And we'll talk about that as biochem comes along, but that's kind of the context. Glucose gets phosphorylated to glucose 6-phosphate. The question states that the standard free energy change for this reaction is delta G naught equals negative 3.99 kcals per mole. And again, recall that the sign on delta G here, negative, means that this is favorable. So this reaction, burning ATP to make glucose 6-phosphate from glucose and ADP as a product, is favorable. This should go forward. And the rest of the question states that a solution of 120 millimolar glucose and 15 millimolar ATP are allowed to react to equilibrium in the presence of the hexokinase enzyme at 37 Celsius. What will the equilibrium concentration of all four components of the mix be? ATP, ADP, glucose, and glucose 6-phosphate. Okay. So it's asking for what are the concentrations at equilibrium of all four components. And the key word there is equilibrium, right? So what's going to tell us about the equilibrium? Well, it's going to be KEQ. And so the first thing we want to do is take our delta G naught, convert that to KEQ. Delta G naught, recall, is the negative RT times the natural log of KEQ. In this case, negative 3.99 is equal to negative 1.987 times 10 to the negative third. What temperature are we at? We are at 37 Celsius. 37 plus 273.15 is 310.15 Kelvin times the natural log of KEQ. Okay, so what we can do here is divide by RT on both sides. What we get is, let's see, 3.99 divided by 1.987 times 10 to the negative third times 310.15 Kelvin. Let's see, 3.99 divided by 1.987 10 to the negative third divided by 310.15. We get 6.47. Is that the right answer? No, that's going to be the natural log of KEQ. And to undo our natural log, we have to do e to both sides. So our KEQ in this case equals e to that 648.36. I'll erase that and make it prettier. 648.366. Great. 648.366. At equilibrium, there's 648.36 times more glucose 6-phosphate and ADP than glucose and ATP. So that's the correct ratio we need to get to. Okay, so I'm going to go ahead and move on to the next page and start working some of this out. Okay. So we have that ratio. Okay, so our reaction, remember, is glucose plus ATP goes to glucose 6-phosphate plus ADP. And these start out at concentrations. Now, we just started out with nothing over here. But over here we started with 120 millimolar and 15 millimolar. Correct? That's our initial set of concentrations. Now what's going to happen here? Well, we have no products and we have a lot of reactants, and so we should predict that this reaction is going to go to the right, which means that these guys are going to go up by their molar equivalents. That's all 1 to 1 here, 1 to 1 to 1 to 1. So these are just going to go up by 1x, or just x. And these guys are going to go down by x. So our final, that's our change. And our final equilibrium concentrations are 120 minus x, 15 minus x, x, and x. So that is our initial change of equilibrium. And so here we're going to run into a final concentration. All we need to do is solve that x. Now how do we do that? Well, one cool thing we know, remember, is our KEQ. In this case, it was 648.36. That is the ratio between products and reactants. So in this case, what we can say is it's equal to product 1 times product 2. We know that those concentrations are just 0 plus x, or x, divided by our reactants. 120 minus x is one of them, and 15 minus x is the other. Alright, so I can expand this guy. X squared on the top, easy enough. On the bottom, we're going to have to do a little bit more foiling, remember, so we're going to have to do this first. That's going to be 1800. We plug that in. Then we'll do minus 120x. Then we'll do minus 15x. And then plus x squared. So our final thing should be 648.36 is equal to x squared over 1800 minus 135x. I'll just redo that. X squared over 1800 minus 135x plus x squared. Cool. So that is our equality. Now we're trying to solve for x. Unfortunately here we're going to have a quadratic. We already have a quadratic in the base. So we're going to have to solve the quadratic equation. So I'm going to go to a new page and we'll start simplifying that. So again, we have our 648.36 equal to x squared over 1800 minus 135x plus x squared. To start to get this all on one side, we're going to need to take this whole denominator, multiply it out by the 648.36. So 648.36 times 1800 comes out to be a large number, 1167048. 648.36 times negative 135 is negative 87,528.6x. And then 648.36 times x squared, hey, 648.36 x squared. And that all equals x squared. So the end of this, we want to solve for 0. So we'll subtract x squared from both sides. And now we get our quadratic. (647.36 x squared minus 87,528.6x plus 1167048. And that all equals 0. Remember, the zeros are the x roots that we're going to be solving here. And of course, you probably recall the quadratic formula we're going to need to solve this, the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And those equal x. So there is our quadratic formula we're going to need to plug into, our quadratic equation we'll need to solve, using our a, the x squared term, the b from the x, and the c in the polynomial here at the end. Okay, so I'm going to go to a new page and we will start solving this. Okay, so I'm going to write our quadratic up so we can look at it. 647.36 x squared minus 87,528.6 plus 1167048. Okay, so I'm going to start plugging into our quadratic. Negative b is positive 87,528.6. That's x too, don't forget that. We don't need that x here, but don't forget it in your polynomial. And it's plus or minus the square root of that squared, which in this case is 7.66 times 10 to the 9th. That's b squared. That's just this squared. Minus 4ac. That's all kind of squished over there. Over 2 times a 647.36. Okay, so what I'm going to start to do when I get this all plugged in is I'll solve this stuff under the radical. Okay, so the square root of, in this case, 7.66 times 10 to the 9th minus 4 times 647.36 times 1167.048. Okay, so we have the square root of 4637.9999227. And I'll go ahead and solve that. End up with 68,102.8577. And that's plus or minus, originally our negative b, 87,528.6 divided by 2 times 647.36 is 1294.72. Great. So that is our key solution. It's got to either be plus or minus that. Okay. So how do we know which one it is? Well, we can just start plugging in. I'm going to go ahead and erase some of this. So I'm just going to take a couple of these. I'm going to do the positive root. I'm going to add these two together. I'm going to add this to this and then divide by that. 87,528.6 plus 68,102.8577 divided by 1294.72. One of our roots is 120.204. Okay, and let's try the negative root. Let's try this minus that. 87,528.6 minus 68,102.8577 divided by 1294.72. Our two roots are x equals 120.204 or 15. Okay, there's some rounding in here. One of these is certainly more reasonable than the other. Remember what our concentrations were. Our glucose was 120 millimolar, and our ATP was 15 millimolar. Okay, obviously we can't lose 100 in our concentrations at equilibrium or minus x. So if we had 120, sure, there might have been a rounding error. We could subtract that from glucose, but then we're going to have millimolar of ATP, and you can't have negative. You have to be limited by your limiting reactant here. So this reaction is going to use pretty much all of the ATP we have. Okay, and then remember our G6P and our ADP just equaled x. So this is the x route that makes any sense. This is the x root that we are going to use. And so our glucose is then going to be 120 minus 115, which is going to be 105 millimolar. Our ATP is going to be 15 minus 15, which is 0 millimolar. Our G6P is going to be 0 plus 15, which is 15 millimolar. And our ADP is going to be 15 millimolar. So we have used up all of our limiting reactant. ATP was our limiting reactant. We have 105 millimolar glucose left, and we end up with 15 millimolar of our G6P and ADP. So we've used it all up. That's reached equilibrium, and that is our solution here. So that's what you would give on an exam. So hope that helps.